1974, two self-funded researchers published photos of radishes triple their normal size and cucumbers ripening weeks early, all from a magnet, not a single drop of fertilizer. The world was told these results were impossible, and then the findings vanished. Who benefits when the physics of plant life is ignored? And do these lost chapters hold the key to permanent abundance? To understand the true power and risks hidden in magnetic fields, we have to start with the evidence they left behind. On page after page of their 1974 book, Albert Roy Davis and Walter Rawls presented black and white photographs that defied the rules of plant biology. In one plate, a cluster of radishes sits beside a control group. The difference is not subtle. The magnet-treated radishes are swollen to nearly 3 times the mass of their untreated siblings. Bulbs so large they crowd the dish, their roots tangled in a dense mat. The caption claims a 200 to 300% increase, achieved without a single drop of fertilizer. No special soil, no chemical boost, just a single magnet, positioned with scientific care. A few pages later, another plate captures a row of cucumber vines. The vines exposed to the south pole of a magnet are already heavy with fruit, while the controls lag behind, their leaves still immature. The book notes that these cucumbers ripened almost 2 weeks ahead of schedule. The only variable was which end of the magnet faced the seeds. Each image is numbered, labeled, and accompanied by handwritten notes, dates, weights, and exact details of the setup. The plates do not hide their ambition. They invite scrutiny, offering a direct visual challenge to the idea that plant growth is governed solely by chemistry. The scale of the anomaly is unmistakable. These are not minor improvements. The results, as reported, are orders of magnitude beyond what conventional horticulture expects from any single intervention. The photographs remain the heart of the claim. They do not explain how the effect works, or why. They simply show what happened when the rules were broken by a force that cannot be seen. The question is no longer whether the evidence exists. It stares back from the page. The next question is how such an outcome could be possible. Albert Roy Davis spent decades chasing answers that mainstream science refused to ask. He was born in 1908. Davis chose to be an outsider, a self-taught physicist who built his own laboratory in rural Connecticut. His earliest experiments in the 1930s had nothing to do with plants. He was searching for a cure to his own health problems, testing how magnetic fields affected wounds and bacteria. The results were strange enough to keep him working when university labs and grant committees turned him away. Walter Rawls entered the story years later. Trained as a chemical engineer, Rawls brought methodical discipline to Davis's relentless curiosity. Together, they set out to test whether the invisible force of magnetism could shape the living world. Their partnership was unconventional in every sense. No corporate funding, no academic backing, no promise of profit. Every experiment was paid out of their own pockets. Every failure was logged in handwritten notebooks. Every breakthrough was captured on black and white film. By October 1974, they had compiled their findings into a book called Magnetism and Its Effects on the Living System. It was published by a small press far from the reach of scientific journals. The book's plates, the ones showing giant radishes and early cucumbers, were the product of this self-funded research. Each image, each note, was a direct record from their homegrown laboratory. Davis and Rawls were not hobbyists tinkering in a garden. They were investigators who believed that the rules of biology could be rewritten if you understood the physics beneath the surface. Their evidence was not just visual, it was a challenge to the chemical dogma of their time. The next step would require looking deeper into the science of magnetism itself and the strange story of how invisible forces shape the soil. Philip Callahan spent his career studying the quiet signals hidden in the earth. As a radar technician turned entomologist, he noticed something peculiar while surveying the fields of Ireland and the volcanic slopes of Hawaii. The most fertile soils, those that produced lush harvests year after year, shared a physical trait that had nothing to do with nitrogen, phosphorus, or potassium. They were paramagnetic. These soils could be attracted ever so slightly by a strong magnet. Not enough to leap from the ground, but enough to register on a sensitive meter. Callahan measured this property in CGS units, a standard of magnetic susceptibility. Fertile volcanic ash or Nile Delta earth often scored above 1,000 CGs. By contrast, exhausted farmland or industrial sand barely registered above 50. In practical terms, a handful of dark volcanic soil would drift toward a magnet, while a scoop of depleted dirt would sit motionless. This difference, invisible to the naked eye, was the hidden signature of abundance. He called this the soil antenna effect. Each particle of paramagnetic rock acted like a tiny radio antenna, tuned to the background energy of the planet. These minerals, basalt, granite, and certain clays, captured and stored the Earth's natural electromagnetic pulses. In Callahan's view, roots tapped into this field, drawing not just minerals, but a kind of electrical nourishment. Where paramagnetism was high, crops grew faster, resisted disease, and required less water. Where it was low, even the best fertilizer could not revive the land for long. The numbers were not abstract. In his fieldwork, Callahan routinely recorded 1,200, 2,000, sometimes even 4,000 seeds in volcanic soils. By comparison, the average American cornfield, after decades of chemical treatment, often fell below 100. The implication was simple but profound. The secret to lasting fertility might be measured with a magnet, not a chemistry set. This was not theory, it was a physical property, one that anyone could verify with the right meter. For Callahan, the Earth itself was a living battery, and the most productive soils were those that could hold a charge. The next question was how this charge affected water, and what happened when magnets were used to amplify the signal. Water, the silent partner in every harvest, moves through soil and roots in ways that are easy to overlook. But magnetoculture claims something extraordinary. A simple magnet could change the very nature of water itself. In Davis and Rawls' laboratory notebooks and later in field trials from the 1970s, water passed through a magnetic field was said to become thinner, less sticky, faster to absorb, and easier for plants to drink. The claim was bold, but the mechanism was simple. Magnets, especially the South Pole, were believed to break up clusters of water molecules, reducing surface tension by as much as 30 to 40%. Modern studies, though more conservative, put these numbers to the test. Peer-reviewed trials from Egypt, Turkey, and Iran used tensiometers to measure the effect. The results showed a consistent drop in water's surface tension, sometimes 15%, sometimes 25% lower than untreated water. In practical terms, magnetized water spreads more quickly through dry soil, penetrates root hairs with less resistance, and hydrates seedlings in less time. A 2020 university study reported maize yields up by 18% after a season of magnetic irrigation with no extra fertilizer. Another greenhouse trial in Turkey found beans sprouted 22% faster and grew taller when watered with magnetically treated water. These are not miracles. They are measurable gains, numbers that can be checked, repeated, and cited. Skeptics argue the effect is small, sometimes within the margin of error. Yet even the most cautious reviews admit magnetic water can boost yields by 10 to 20% in controlled conditions. An independent soil scientist observed that paramagnetic soils enhance structure, and magnets may mimic this by aligning water molecules and making hydration more efficient. The physics is subtle, but the outcome is clear. When water is structured by a magnet, roots respond as if they have been given a shortcut. This is the practical edge of magnetoculture, an invisible adjustment anyone can replicate, and that modern science, in its most careful trials, has quietly confirmed. A meta-analysis from 2020 is cited. The numbers are real, the effect is modest, but the principle stands. The laws of physics, not just chemistry, are at work in every drop. From 1945 to 1975, the economics of agriculture underwent a transformation that can be traced in numbers more than words. In 1945, American farmers spent $300 million on commercial fertilizers. By 1975, that figure had surged past $3 billion, a tenfold increase in just one generation. The volume of synthetic nitrogen, phosphorus, and potassium applied to fields rose in lockstep as wartime chemical plants pivoted to feed the Green Revolution. Crop yields soared, but so did the industry's dependence on annual inputs. At the same time, scientific curiosity around magnetic agriculture was quietly shrinking. In the early 1970s, academic journals and conference proceedings carried a handful of papers on magnetoculture each year. Within a decade, that number had dropped by over 90%. Citation graphs show a steep decline. What was once a small but persistent trickle of research nearly dried up as fertilizer sales broke record after record. The contrast is stark when plotted side by side. As fertilizer revenue climbed, attention to the physics of soil faded from the scientific record. The correlation is not just anecdotal. Analysis of publication databases and USDA statistics points to an inverse relationship, one curve rising, the other collapsing. The numbers do not explain motives, but they anchor the reality of what was valued, funded, and pursued. The era of physics-based farming was not ended by a single discovery, but by a shift in economic gravity. The next question is why a tool that promised permanent fertility was left behind in favor of one that required constant purchase. A permanent magnet costs less than $5, and it will outlive every tool in the shed. A single bar, once placed in the right spot, keeps working for decades with no maintenance and no further purchase. Compare that to the current model, a bag of chemical fertilizer priced at $50 or more per acre, emptied and replaced every season. For the companies that supply these inputs, the logic is simple. Recurring sales mean recurring profit. The magnet, on the other hand, is a one-time sale. A product that once delivered removes the need for repeat business. Trade groups and agricultural extension offices rarely mention magnetoculture in their bulletins. When they do, they usually warn that it is unproven, not supported by current science, or not recommended for commercial growers. The official line says physics-based methods lack the robust data required for industry endorsement. But behind the language of caution is a structural incentive. The chemical model keeps farmers on a subscription plan, tied to products that must be bought again and again. The magnetic method threatens that cycle. It offers a way out, a tool that cannot be patented, branded, or locked behind a paywall. This resistance is not just about skepticism. It is about protecting a system where every acre, every year, means another transaction. For those willing to experiment, the cost gap is impossible to ignore. The only barrier left is the willingness to try. A single bar magnet, a compass, and a few minutes of careful setup. That is all it takes to test the claims made by Davis, Rawls, and Callahan. The first step is always polarity. Every magnet has a north and south pole, but only one side accelerates growth. Place a compass flat on the table and bring one end of the magnet near the needle. The needle's north end will be drawn to the magnet's south pole. Mark this end clearly. Mistaking north for south will stall or even kill your seeds. This is not a detail to skip. The seed charger method is the simplest. Pour your seeds, radish, bean, or cucumber, into a shallow dish. Then rest them directly on the marked south pole of the magnet. Seal the dish to keep out moisture. Leave the seeds for 24 hours. This window is critical. Too short and the effect weakens. Too long and you risk desiccation. After a day, plant as usual. Expect to see sprouts up to 4 days faster, with more seedlings breaking through. In Davis and Rawls trials, germination rates jumped by as much as 20%, and early growth was noticeably stronger. For water energizing, attach a magnet to your garden hose, south pole facing inward. Secure it with tape so the water flows past the active phase. Keep the flow steady, no faster than 1.5 gallons per minute. Higher speed disrupts the field, reducing the effect. This magnetized water absorbs into soil more quickly, reaching roots that might otherwise stay dry. Field studies and home trials report 10 to 20% faster moisture penetration and improved early vigor, even without fertilizer. To build a magnetic ring for a tree, bury 4 magnets in the soil. South poles aim toward the trunk. Space them evenly in a circle, about 1 to 1.5 meters from the base, 5 to 10 centimeters deep. This setup mimics the paramagnetic fields found in volcanic soils. Fruit set can arrive a week or 2 early, and the tree's overall health often improves. If the magnets are misaligned or the wrong pole is used, the effect is lost. Every method depends on getting the polarity right. Always confirm with a compass before you start. These are not toys, they are tools. And the difference between success and failure is measured in millimeters and minutes. Germination tests reveal the difference between theory and practice in a way that numbers alone cannot. 10 radish seeds, placed on the south pole of a magnet for 24 hours, break soil 2 days ahead of schedule. Their stems are thick, leaves broad, and by day 7 nearly every seed has sprouted. 9 out of 10 on average reach for the light. In the tray beside them, exposed to the North Pole, only 3 seeds show any sign of life. The rest remain sealed, as if winter never ended. The control group, untouched by magnets, falls somewhere in between, with 6 or 7 seedlings, slow and uneven, and roots that hesitate to branch. This pattern repeats across 3 backyard plots. The South Pole group averages 87% germination. The North Pole, only 28%. Controls hover at 65%. By the end of 2 weeks, the south-treated plants are not just taller, they measure 54 millimeters on average, compared to 45 for controls, and a mere 31 for the North Pole. These are not accidental outliers. The numbers line up with Davis and Rawls' original reports, and with conservative university trials that followed decades later. The effect is not limited to radishes. Beans, cucumbers, even wheat respond in the same way. When the wrong pole is used, the failure is immediate and severe. In one split trial, a tray of north-exposed bean seeds shows a 70% drop in germination. The lesson is clear. Polarity is not a footnote. It is the difference between a garden that thrives and one that never starts. Replicating these results at home is simple, but the margin for error is unforgiving. A misplaced magnet, a reversed pole, or a weak field will erase any advantage. The raw numbers speak for themselves, but the real proof is in the failure. When the rules are followed, growth accelerates. When they are ignored, nature stands still. Today, chemical fertilizers dominate nearly 90% of global agriculture, while the physics of paramagnetism remains locked out of mainstream practice. The question is not whether magnets can grow bigger plants. The question is why open-source solutions threaten billion-dollar industries. Earth's pulse is still free. The harder it is to patent nature, the more vital it is to remember what cannot be bought. Share your thoughts below.